and we're very pleased to have with us. I'm exceptionally pleased because we did have a few minutes when we were a little bit worried about delays with Jun turning up, but we're very pleased to welcome Jun Kai as our speaker tonight, fresh from a week in Madrid, I believe. So,
yes.
Bienvenido a Qiong. Now, Jun is a fellow of the Royal Society of Chemistry and a professor in sustainable energy and materials at the University of Surrey. She's got a master's degree from Tsinghua University in China, a PhD from Edinburgh, and she was a research associate at Imperial London. She's worked on lots and lots of projects, including EU projects, and at the moment she is currently leading a team of 5 research fellows and 6 PhD students, and apparently they've all contributed to her 125 peer-reviewed research papers. So we're very pleased to welcome Qiong tonight, and I shall now step back until question time and pass the floor to you.
Thank you, Brad. Well, we had a bit of drama, but I'm very pleased to be here, and it's my pleasure to talk about batteries. Let me start with that image showing the first generation lithium-ion batteries, where you have a lithium cobalt oxide as cathode and graphite as anode, and basically you move the lithium ion between the 2 electrodes and you do the charge and discharge. So there are 3 giants behind this development. Professor Stanley Whittingham, who proposed the rocking chair mechanism. He said if we could manage to find some material to host the lithium ion and manage to move them in between, we could create rechargeable batteries. And Professor John Goodenough, when he was at the University of Oxford, invented the lithium cobalt oxide as cathode and provided the host for lithium ion battery for lithium ion. And it was until 1990s where Professor Akira Yoshino, who created the first safe lithium-ion cells using carbon as anode, combined with correct electrolyte. And 3 of them, because of their significant contribution, they were awarded 2019 Nobel Chemistry Prize. Why lithium-ion battery have dominated the portable electronics and the electric vehicle applications? This is because they have very high energy density and also very high power density. So energy density is to do with how long the battery can last, and power density is to do with how fast you can get the power. And you can see that actually, although lithium-ion battery has a lower energy density compared to internal combustion engine and fuel cells, it has excellent power density, outperforming most the previous batteries, including lead acid and nickel metal hydride. So that's why we're using them a lot. They really transform our life. However, we always want more. And so if we look at the energy density at the moment, most of the commercial lithium-ion battery are below 300 watt-hour per kilogram. And that means that probably we can drive our electrical vehicles for 300 kilometers. But what if I want to drive from London to Edinburgh without having to charge? Then I need some batteries with higher energy density. So there has been a lot of push towards developing high energy density batteries. Currently, I think the best one is probably 700 watt-hour per kilogram. And I just want to do some simple reminder here that energy density is a contribution from the storage capacity and the potential of the materials inside. So let's look at the cathode material first. And we did some review a couple of years ago, mapping different cathode material in terms of their specific capacity and also their potential. And if we compare them, these are the 5 most popular cathode material on the market. You can buy them available. These are the materials available on the market. And we can see that the first generation lithium cobalt oxide, LCO, has quite high energy density, but the rest of the performance index are not very good, where the new generation, the nickel cobalt manganese and the nickel cobalt aluminum one, they provide both high energy density and also better performance matrix in terms of lifetime and safety. Where the LFP lithium iron phosphate is interesting one because it doesn't contain any critical elements there, and although the energy density is not so good as NCM and NCA, it has very high safety and a very high lifespan, and therefore it has attracted a lot of interest from car manufacturers, including Tesla. So those are the cathode materials available on the market, but we want better ones. Therefore, there has been research into the lithium-rich candidates. Here you can see that they have much higher energy density compared to the other ones that I mentioned just now. However, there are some challenges with those new materials. So my PhD student Qiong tried to improve the performance of this lithium-rich cathode material, cobalt-free. They typically have a very bad voltage decay, as you can see the black line. So what she did was try to dope ruthenium into this material, only 0.03% weight, and it significantly improved the voltage stability. So that's all just, I like the fancy high resolution TM images there showing that the material is what we have produced. Okay, so cathodes play a very important role. We want high storage capacity, high potential for cathode, but anode material also very important. For anode material, we want them to have a very low potential so that we can then have high voltage of the cell and at the same time high capacity. Now graphite has been very popular there, you can see, because it has a very low potential. But of course the storage capacity is not so high, but the advantage of graphite is it's very, very stable, so it provides thousands, 2,000, 3,000 of cycles. Now, if you want to have a higher storage capacity, then you go for the alloy type. Typically, silicon and tin have been used, and also lithium would be the ideal candidate, and I will talk about them. Now, the problem with alloy type material like silicon or tin is when they intercalate lithium, they have huge volume expansion. For silicon, that's 400%. And that huge volume expansion will cause crack and therefore particle break down and therefore lose contact. So performance decay, and there has been different strategies try to improve this, trying to make silicon into nanoparticles, nanowires, or use the host material, and also maybe try to use self-healing binders and some solutions try to repair the material. And I show you here, this is a US company, this is a spin-out technology from Stanford University, where they have successfully managed to integrated silicon anode in the lithium-ion battery, and they achieved very high energy density, 500 watt-hour per kilogram, and very high power density, and can charge at a very high C rate, and has a charge very quickly and good safety. So there are products available on the market now. Of course, the ultimate choice for anode would be lithium metal, because it has the highest theoretical storage capacity and the lowest potential. That's the ideal anode we want. However, it comes with a lot of challenges because lithium metal is very reactive. It can react with all the oxygen and moisture in the air, and therefore you have to handle them very carefully in vacuum condition. And it's not very easy to create that kind of vacuum condition. So we have glove box in our lab, but you can only make batteries in a very small scale. Apart from that, lithium metal also react with the liquid electrolyte to form SEI, that's solid electrolyte interface, and that SEI layer will continue to increase. And also some of the lithium become pulverized and become particles, and you lose some of the lithium. And what's worse is the lithium dendrite grow at the interface, and once you have that dendrite, it can come to cathode, and then you have short circuit and your battery die. So in order to improve that performance, then there has been a lot of work trying to prevent that dendrite growth, and one of the strategies is to develop electrolyte. And of course, in the traditional batteries, first generation lithium batteries, the electrolyte is the salt, LFP-F6, dissolved in a mixture of organic solvent, with a small amount of additives that's to enhance the stability of the battery. There has been a lot of work trying to develop a different kind of electrolyte in order to prevent that lithium dendrite growth. At least here, there's a lot of properties that we want from the liquid electrolyte. They must be stable under that voltage condition, typically 4 volt for the cell, and then they need to have a good mobility of lithium ion within that liquid electrolyte so that it can move between the two electrodes, and they need to have some kind of thermal stability. But however, currently the organic solvents, they are very easy to combust. That's the issue with the safety with the liquid electrolyte lithium-ion batteries. And so to have safer batteries, people have now come up with the idea to develop solid polymer electrolyte to replace that liquid organic-based liquid electrolyte. Advantage of that is because polymer materials are very flexible. So because of that, you can now make your batteries into wearable devices. You can wear them as a smart watch or flexible phones, etc. So they have this kind of application. Polymer electrolyte, the solid polymer, normally have much lower lithium conductivity, and therefore the power density is not so high compared to the liquid electrolyte-based one. And so scientists have come up with, I should go back, come up with another solution, which is the inorganic solid-state electrolyte, which is based on ceramic materials. And over the past 10 years, there has been a lot of development to achieve very high lithium conductivity within that solid-state electrolyte. And now you can have some materials that have even similar lithium-ion conductivity compared to the liquid electrolyte one. So in the middle is the solid-state electrolyte, and then you have the cathode, which is the active material mixed with solid-state electrolyte particles, and then you can have the normal anode, or you can use lithium metal now as the anode. The challenge with this type of battery is it's not very easy to fabricate the dense ceramic thin film, typically around 100 micrometer. It's very thin, and it does require a lot of art and experience to make that kind of ceramic thin film, very robust one, because they are very easy to crack, especially in the solid state, this kind of solid state batteries. there's all of the material, the inside are particles, solid particles. So in order to create the good contact, then you normally have to apply pressure. And under pressure, the ceramic material could crack. Another challenge is then the people thought, before they proposed the idea of this kind of inorganic solid state electrolyte battery, they thought this could prevent lithium dendrite growth because now you have dense ceramic layer. However, recent research found that lithium dendrites still grow, although at a much slower pace. We now come up with another idea. Instead of using lithium metal as anode, we say maybe we can use interlayer material here that can alloy with lithium metal and then to accommodate lithium metal there and to enable the stable charge-discharge process. So that's what we are doing. Within this Horizon Europe funded project, we're developing solid-state batteries without lithium metal at the fabrication stage. And that will make the fabrication process much easier because, as I said just now, lithium metal is very sensitive to air, and so fabrication process will be much simpler, and also the energy density would be much higher. But there are still technical challenges, so within this consortium, we work with another 11 partners across Europe to tackle the technical challenges, and our aim, our task is to use computational modeling to help select the best interlayer material that can enable very stable battery performance. Now I'm coming to another type of battery, still use lithium metal as anode, but the cathode now is completely different. The cathode material now is a sulfur. And we all know sulfur is very cheap and very abundant and also light. So it does provide a lot of advantages for this type of battery. The challenge is, though, you have the conversion of the sulfur molecules. So the sulfur molecule in the initial stage is S8. And it will go through a series of conversion reactions to create polysulfide molecules, and those polysulfide molecules are soluble in liquid electrolyte, so they dissolve in the liquid electrolyte and migrate to the anode and react with lithium metal, and so there's a very bad degradation happening there. This is the Faraday Institution funded project involving a lot of UK universities, and we are one of the partners who are trying to solve the challenges with this battery. So in the first phase, we are trying to develop some cathode material that can trap lithium, the polysulfide molecules at the cathode, at the same time facilitate the polysulfide molecule conversion. The second phase will be look at the anode side. So what we did was, so one of the material we proposed is called single atom catalyst. So basically you have a transition metal as the active site and sitting in a carbon matrix, carbon lattice, surrounded by 4 nitrogen atoms. So what we found is the vanadium and tungsten-based ones give very strong binding energy for the polysulfide molecules. Therefore, we think they should be able to trap the polysulfide molecule there. We also looked at the reaction pathway for the polysulfide molecule conversion, and then also the activation barrier for the conversion. And we found that, again, the vanadium and tungsten-based ones, they provide lower activation barriers, so meaning that they will be able to speed up the reaction process. So that's one material we proposed. Now, working with the group at University of Cambridge, they proposed a molybdenum disulfide material as cathode, and they compare with different materials, and they found this lithiated molybdenum disulfide give the best performance in terms of storage capacity, the red line, and also the cycle number of cycles. So that's Professor Manish Chowala, who is leading this project, and his postdoc, Dr. Zhuanan Li, who did the beautiful work here. And they compared their battery performance with all the ones reported in the literature on lithium-sulfur battery. And their work, the red star one, really stand out compared to all reported in the literature in terms of the volumetric loading, well, the capacity, so the storage capacity. And when they compare with other lithium-ion batteries based on other materials, again, this material really stand out in terms of volumetric energy density and gravimetric energy density. So they have filed a patent. I'm presenting it now because they have published their results on Nature Energy, so I can share with the public. So they have trying to commercialize this material for lithium-sulfur batteries. Okay. So I've covered several lithium-based battery technologies. But we have a challenge, critical challenge with lithium reserves. Most of the lithium are in the South America, the Golden Triangle area, and US and China. So this creates some supply issue. Furthermore, if we look at the electric vehicle demand, it increased over the years, increased a lot, and it predicts that 22 million tons, we only have 22 million tons total lithium reserve, and for each electric vehicle you need 8 kilo lithium to be in the battery, and in order to hit net zero by 2050, we need 2 billion EV on the road. And if we do some simple calculation, the lithium reserve is not enough. And plus, to take the lithium from the mine, from the rock, it requires average of 15 years to develop into practical application or operation stage, and it take a lot of water during that mining process. So, for example, the Bolivia's San Cristobal mine uses 50,000 liters of water a day, and that's a huge burden on the water resource. We all know that, we have a pressure on water. Therefore, that's why we have been trying to develop alternative technologies that can work as, but also replace lithium-ion battery. And one of them is sodium-ion battery. Basically, it works very similar to lithium-ion battery by moving you only just move the sodium ion instead of lithium ion in between the two electrode materials, anode and cathode. And of course, the kind of material here is different from the lithium-ion battery because sodium ion is bigger. So you can get abundant material supply with sodium. You can get sodium from the sea, and you can get anode as hard carbon from biomass waste, and cathode material there are a few candidates here. You can when you look at them, you can see none of them involve cobalt. Cobalt is a critical element, and so you can have cobalt-free material. So because of this, sodium-ion battery is low cost and sustainable. And one advantage for sodium-ion battery is that they have very good performance at low temperature, minus 20 degrees C. when lithium-ion battery has only 60% of capacity retention at minus 20 degrees C, sodium-ion battery can achieve 90% capacity retention. So it does have a lot of advantages, and I just want to show some example what we did. 6 years ago, we got a funded project from UKRI to investigate what kind of hard carbon, what kind of structure we want from hard carbon in order to have a good performance for sodium-ion battery. And that's my postdoc, Dr. Amelia Olsen, who is now assistant professor at University of Amsterdam. And we looked at a range of possible structures for the hard carbon. So hard carbon can have a mixture of all these different structures. And yeah, Amelia did a great work and published a lot of work. I just want to show you one example here is we looked at the defects in hard carbon. So if we make hard carbon from biomass, inevitably they will contain some impurities, oxygen and nitrogen and hydrogen. But what kind of defect structure are there is not very clear. Experimental technique, very difficult to probe them. So we use we create some computational models, and we calculate the formation energy, and we then propose that those ones with low formation energy could be the possible defect structure we have. And when we look at the absorption, we can see that they all provide stronger absorption of the ions. So meaning that they will probably give higher storage capacity. But if we think about how ions move within the material, we don't want very high migration barrier. And so the nitrogen doped one doesn't have very high migration barrier, but the oxygen one create big migration barrier, meaning that the sodium ion could be trapped there, which is not good for charge-discharge process. So we don't want a lot of oxygen ion there. We also looked then at the interlayer distance of the structure, and then we found that the favorable intercalation, which is when the energy is below zero line, only happen at a certain interlayer distance for sodium and for potassium. But for lithium, it doesn't matter. You can put lithium into any interlayer distance. So we then collaborate with a group at Imperial College London, and we then we suggest some structural properties to them, and they made the hard carbon from the biomass, glucose, and then carbonize at different temperature, and then found that the one carbonized at 1,500 degrees C give the best storage capacity because they have limited amount of oxygen defects and also the good interlayer distance. And then we propose this mechanism that we need certain amount of oxygen defect there to improve the storage capacity, but at the same time we need a suitable interlayer distance and a pole size in order to increase the storage capacity. So there are a good number of companies across the world developing sodium-ion batteries. One in France, Tiamat, and one in UK, Faradian. And I'm showing here this Chinese company. It's the biggest battery manufacturer in China, CATL. They also, in recent years, started the development of sodium-ion battery. And the first generation was launched in 2021 with energy density of 160 watt-hour per kilogram. They are aiming for achieving 200 watt-hour per kilogram for their second generation batteries. And I took this from their website. They try to compare this sodium-ion battery with a lithium iron phosphate-based lithium-ion battery. So I mentioned this type of material earlier, that this battery has a relatively lower energy density compared to other lithium-ion batteries, but has higher safety and longer lifetime. And if you compare sodium-ion battery with this type of lithium-ion battery, you can see that or it's only that the energy density is a bit lower than this type of lithium-ion battery, but the safety, the long lifetime is comparable, and the fast charging and low temperature performance is even better. So it does provide some promise to replace lithium-ion batteries in some of the applications that you don't require high energy density. Another type of battery is the redox flow batteries. There you have very simple cell structure. You have for both anode and cathode, the black ones, they are just the carbon materials. And so it could be relatively much cheaper. And the electrolyte is stored outside in the tanks. You can then use pump to pump the electrolyte through the electrode for the electrochemical reaction. The good thing about this type of battery is they have long cycle life, typically can reach 10,000 cycles, where the typical cycle life for lithium-ion battery is probably 3,000 cycles. Yeah? And then the long lifetime, probably 20 to 30 years. This is what we would like to have for grid energy storage, to store energy from the renewable solar and wind, and then supply to domestic or industry application. And also because they don't involve organic solvents, so they have high safety and low cost. The disadvantage of this type of battery is they have much lower energy density and low voltage, because typically they use aqueous electrolyte. With water, you cannot reach very high voltage. And again, just to show some example of what we did for this type of battery, we try to find the best carbon material that can function as the electrode. And those are from the commercial suppliers, the Flünig paper, SGR paper, carbon cloth, all of them are available on the market. And what we did is, in collaboration with Imperial College and MIT, we try to understand which structure would be better and why. So the Imperial College group did X-ray tomography scanning of those materials, and that are the pole size distribution for each of the material. You can see they are quite different. Flünig paper has a very narrow pole size distribution, around 20 micrometer. Well, the carbon cloth also has a narrow pole size distribution, but it has a small portion of bigger poles. SGR paper has very random pole size distribution, and all these are going to affect their performance. So we then built a computational model trying to capture all the processes happening in the electrolyte that include the electron transport in solid fibers and electrochemical reaction at the surface of the fiber, and the liquid electrolyte flow in a porous space and the formation of bubbles. And now we can look at the pressure drop. So I'm in chemical engineering department, and the pressure drop is a critical matter here. If you have a low pressure drop, meaning that you will have lower energy consumption to run this battery. So we want lower energy, lower pressure drop. And you can see that both the SGR paper and the carbon cloth has a lower pressure drop because they have bigger poles. And then when we look at how the electrolyte distribute within the electrode, we found that this SGR paper, so remember it gives a low pressure drop, but as this SGR paper, because the random pole size distribution, part of the structure becomes inaccessible to the liquid electrolyte, so you have a very big concentration gradient across the structure. That is not good because it will give you very high concentration over potential. So in conclusion then, we think carbon cloth is the best candidate for this type of batteries. Okay. Finally, I want to talk about this aqueous batteries, aqueous zinc-ion batteries. Recently, U.S. government announced a big consortium funding, which is for aqueous batteries. This is because aqueous batteries use water-based electrolyte, very safe and low cost, and so it has a lot of promises. So this zinc-ion battery typically use zinc metal as anode, and you can have a few different choices for cathode, and I show them here. You can see probably the manganese oxide one, probably the most promising because it has very high capacity, storage capacity, and also good potential voltage. The challenge is though, when you look at the capacity, then you know that this type of battery can have quite good storage capacity. The challenge is you have lithium metal similar to lithium, the zinc metal similar to lithium metal, you have dendrite growth there. So you want to prevent that. And because you use water-based electrolyte, you have a narrow voltage window, because once you reach voltage 1.23, you will have electrolysis of water reaction happening. You generate hydrogen and oxygen. You don't want that. And also because of its aqueous electrolyte, the temperature is a problem. If you want to go to below 0 degrees C, water become solid. There has been a lot of research in recent years trying to develop electrolyte that can operate at wider temperature range, so then that then will widen the application case for aqueous zinc-ion batteries. And we did this review 2 years ago, and you can see a lot of candidates, electrolyte candidates, has been proposed. And in one of the PhD projects in my group, my PhD student tried to come up with this idea of adding this G2 molecule into the aqueous electrolyte solution. And you can see there at even at minus 60 degrees C, with 60% of that G2 molecule in the liquid electrolyte, the electrolyte still stay liquid, crystal clear. But without that G2 molecule, then it freezes and becomes solid. And it gives very stable performance, cycled up to 1,200 degrees cycles, and much stable compared to the other candidates so the one without this G2 molecule. And this is because the electrolyte with this 60% G2 molecule maintain quite relatively stable lithium-ion conduction mobility within the electrolyte, where the one without G2 molecules has a significant drop of the lithium mobility, zinc-ion mobility, once you reach temperature below 0 degrees C. It shows, some promise for this type of batteries. And if we develop new materials, then we can improve the performance at both lower temperatures and also higher temperatures. Okay. Next, I'm going to move to battery recycling. So this is applicable to both lithium-ion battery and sodium-ion battery, and because no matter which batteries we are going to use, we are going to end up a lot of e-waste, a lot of batteries in the land waste. That's part of the reason we need to recycle them, and the other reason is for lithium-ion battery, for example, there are a lot of valuable materials here. So these are the common material here, and you can see the price on the market. They are very valuable materials. So if we can recover them, then we can make some profit. Just to go through the overall process for battery recycling. So first of all, you need to collect the battery there, and then you need to crush them and probably separate the current collector from the cathode, anode, and separator, and then you go through the safety and clean crushing process. Sometimes if the battery comes still with some storage capacity, then you need to make that storage capacity to zero by applying some technique. And then you come to this all these crushed materials, non-metal, magnetic, metal, black powder, and non-magnetic metals. And particularly the black powder contain a lot of valuable materials. And so currently there are a few different methods trying to recycle the battery materials. One of them, let me start from this one. So this is the pyrometallurgy method, where you basically burn them at a very high temperature, and then you apply the reductive smelting process, trying to put some reductive agent. And this typically happens at a very high temperature, could be up to 1,400 degrees C. And during that process, because it's burning, so you release a lot of hazardous gases, and that high temperature is very energy intensive. So you can recover some transition metal alloys from that process, but as I say, it's a very energy intensive process. Currently in China and also in Asian countries, this is the method that is commonly used. This is the hydrometallurgy method, where you apply some kind of acid or alkaline medium, so chemicals, and you can have reactions at relatively low temperature, probably room temperature, or maybe below 100 degrees C, and then you can recover the materials. So this is now being applied at a larger scale. But of course, because you involve liquid solution to do that recycling process, so you generate liquid waste. Another method is called the direct recycling method. So this is when we have cathode materials and there's some damage to the cathode material. So the value lies mostly with the cathode materials. There's some crack maybe in the cathode materials, or the cathode material maybe lost some element, and you use some chemicals to repair that cathode material. So it happened at relatively mild condition, and therefore you can achieve very good recovering efficiency and also environmentally more benign, more environmentally friendly approach. So the direct recycling approach at the moment is probably the most promising, but then you will need to make them to large scale application. So the idea is, so I'm borrowing this image from CSC and Qiong, a Spanish energy research institute, who developed a direct recycling method. So the idea is we work together where the end users aware of the recycling issue, so and the batteries are collected properly, and then so the material coming from the mining, and you refine them and you make batteries, and when they finish their life of the battery, then you can recycle them and back to the loop for secondary use. And then by doing that, you reduce the landfill waste. And hopefully we then can build a circular economy by doing the recycling. Okay, I'm coming to the summary of my talk today. To summarize, lithium-ion batteries, we want more energy density and power density from them. Therefore, there has been a lot of development, cathode, anode, lithium metal, solid-state electrolyte. Sodium-ion battery could be a promising alternative and more sustainable and low cost. Redox battery could be well suited for medium to long duration grid storage option, but we need to improve probably the energy density. The aqueous zinc-ion battery could be another alternative as low cost and sustainable candidate. And if we develop a new electrolyte, we can widen the working temperature range. And battery cycling is necessary and important. Okay, thank you for your attention. Not too long.
Roger, thank you very much indeed. So, we'll pass on that for the moment because the battery seems to be flat or something.
We need better batteries.
Clearly we need better batteries. So, that was a fascinating 45 minutes of very, very intense facts as far as I was concerned. Does anybody have any questions that they'd like to raise with Tom? And Mike has a microphone that you can speak into, hopefully with a working battery.
Do you think that sodium-ion batteries will replace lithium-ion?
I think they can be a good alternative for certain applications when you don't require high energy density. So if you just drive your car maybe for short distances, then they could be a good alternative. But lithium-ion batteries do have it's still the best in terms of energy density and power density. So they still have a lot of application scenario. I think we need to work on both of them.
I was also curious about, you said it takes 15 years to develop a lithium mine.
Yeah.
That's a long time, isn't it?
It is a long time.
Can you elaborate on why it takes so long to do that?
I'm actually not very sure. This is what I learned from the literature and from some company reports. But I'm not an expert in mining, so I'm not entirely sure why it takes so long.
I think it's Toyota have been talking about a solid-state battery coming out in 2030. They now pulled it back to 2027.
Yeah.
When they say solid-state, do we have any, I'm sure they're keeping it fairly quiet, do we have any sense of what actual material it will be, and roughly, is it likely to be as successful as they seem to be intimating?
Yeah, so there has been a lot of promises about solid-state batteries. Maybe sometimes oversell or overclaim the performance. Actually, I think the CEO of CATL gave a talk recently. He honestly confessed that solid-state battery is currently cannot be practical yet. So if we talk about technology readiness level, that is a term that we use to describe whether technology is ready for the market. If we want technology to be ready for market, we need to TRL reach level 9 or 8. But he said, although his company has invested a lot in developing these solid-state batteries, their TRL level at the moment is just 4. So there's still a lot to do. Now, in terms of what kind of materials, some people cheated a bit. So what they did was they tried to in order to enhance the contact between materials within this kind of solid-state batteries, they actually put a little bit of liquid electrolyte inside. Then it becomes semi-solid. So to make good performance, but then it's not pure solid-state batteries. There are a few candidates good for solid-state electrolyte. On the market available is the lithium lanthanide zirconium oxide, and this is a ceramic and very brittle material, easy to have a crack. Another one is called sulfide. So at the moment, probably this is a very promising one because this material relatively soft and easy to process, also very high with very high ionic conductivity, lithium ionic conductivity. But there are still technical challenges to solve. As I say, a lot of challenges to do with lithium metal.
In your experience, from going from TRL 4 to 9 in this sort of technological development cycle, is that a 1 year, 10 years?
I don't think 1 year can do. Maybe 10 years.
Mike, over here.
Hi, thank you for your talk. You talked about, I think it was the world having 22 million tonnes worth of lithium available. What kind of confidence do you have on that? I mean, in terms of oil exploration, people always quoted like certain levels and then people found more, etc., etc. I mean, do you really think that 22 million tonnes is, I mean, I don't know how anyone comes up with such a figure, but is it, I mean, how realistic is that figure to be taken and used?
Yeah, that's a very good point. I have to say that that number may be changing over time, as you say, maybe new lithium mine being discovered with time. I think recently there was a new lithium mine being discovered in Europe. I cannot remember which country now, but definitely there's new mines being discovered with time. So that number is changing. I got that number from, again, a company doing the survey and on the lithium-ion battery market. And yeah, that will be changing. But I think, but at the same time, we also are consuming more lithium mines. And the challenge is also the mining process, energy intensive and waste a lot of water. So there are a lot of issues. And I think ideally, if we can recycle lithium-ion batteries, those will be cheaper options for compared to the mining process.
I mean, the figure just seemed quite small, because cars are not going to be the only market. I mean, everybody wants batteries.
Yes.
So, so there seems to be. I don't know if this is why Elon Musk wants to go to space, but there's
maybe
a need for a lot more. I mean, at the moment, lithium is the only one that's really providing any high energy capacity.
Yes.
Low kilowatts,
Yes.
etc.
Yes. Well, that's why we have been searching alternatives, and yeah, the fact that U.S. launched a new battery program to develop all the battery technology rather than lithium-ion battery is an indicator that we need all the battery technologies.
Can I ask an extension on that question? You had a model for growing demand for batteries. You had a model for the availability of lithium. And unless there is a replacement, there's going to be an almighty crunch where supply is not available to meet demand.
Yeah.
Do we know when that is? 2032 or, you know, is there a...
I don't know. Yeah, this I don't know.
Okay.
Sorry.
Mike, there's another one here.
Hi. With all the incredible research that you've been carrying out, yourself and your colleagues and all the universities around the world, are we at a stage yet where you think we will get to a point to have the perfect battery solution available for commercial use in electric vehicles to increase the worry about range anxiety? And also, that battery, whether it is, will that be the perfect battery for home energy storage systems?
For the driving range, I think increasing the energy storage capacity, density of lithium-ion battery or all batteries is not the only solution towards that problem, because there's a limitation with that, depending on the materials. Very complex physical chemical process happening within batteries. So there's a limitation in terms of how much you can achieve with materials, with new materials. Therefore, this should not be the only solution. Well, the other solution could then be the charging points, building the charging infrastructure. I think the UK is well placed for doing that, because I notice a lot of service stations along the highway, where when I go to Europe, for example, very difficult to find the service station. Well, if you have a service station, then you can build charging points there, so relatively easier. And then another thing is about other technologies. For example, by smartly manage the batteries and the driving habit, you can improve that efficiency and maybe make the batteries last longer. So I have some colleagues, for example, at Imperial College, working on battery management system and a thermal management system, which I didn't talk at all today. Another example is that there are other technologies out there which can provide longer driving range. For example, fuel cells. The energy density of fuel cells is higher, and the charging so the filling of hydrogen is much faster, seconds of a few minutes. The problem is at the moment, fuel cells are too expensive, and lifetime is not so good yet to reach the mass application on the market. But some car companies are still quite optimistic about that type of technology. One possible scenario is you have a hybrid power system. Then maybe you hybrid fuel cells with batteries. And when the car is driving at constant speed, you use fuel cells to provide that constant power. And then when you accelerate, you use batteries to provide that acceleration. And then both power systems will last longer. But of course, it requires a lot of engineering development into it. That's my opinion for this.
Question here.
Thank you for the good talk, very interesting. And it looks like the whole world spent lots of money on the development of this.
Yes.
So my question is not what other audience asked, the lifetime environmental impact of battery industry. So that's one issue. The second issue is mileage, how many miles you can drive for charging. So my actually biggest concern is safety. As lots of people have already heard in the public, BYD has recalled tens of thousands of electric vehicles, and some Chinese car parks reject EV to park or residential buildings as well. So that's just so. What do you think? The first part of the question is what are the causes, fundamental causes of the safety issue when you use battery, either in the car or energy storage station. So fundamental causes. Secondly is, how do you compare the batteries used by different manufacturers such as BYD, German car, the BMW, or Tesla, American car? Just use three as an example. Compare the safety performance.
I will answer the first question, which is probably easier. So there are a lot of processes happening in the battery during the charge-discharge process. Now, during discharge, lithium-ion get out of the graphite material and move to the cathode side, so get into the cathode. During charge, lithium-ion move out of the cathode material and move to the anode side. Now, when you move lithium-ion out of the cathode material, these are the crystal structure. This material have crystal structure. And when you move lithium-ion out of that structure, sometimes it can cause the crystal structure to become, basically the crystal structure will be broken. And you lose that kind of ordered structure, though you damage the material, and the transition metal could be dissolved from that cathode material. And when you have that process happening, then because if we can see that most of the cathode materials are actually metal oxide, based on metal oxide, and when you have that transition metal and lithium coming out of that lattice, then you have oxygen release. And once you have oxygen in your batteries, it can ignite and react with electrolyte, because you have organic solvent electrolyte. They can easily react with oxygen. And plus, that charge and discharge process, because it's a lot going on when you move lithium out and in the material, you have some resistances that the system need to overcome. And those resistance now convert into thermal energy. So you have a temperature increase. So temperature increase plus oxygen release will cause, if these are not properly managed, if you don't manage the temperature very well, if you don't limit your battery to only operate at a certain voltage window and only charge it at a certain below 100 SOC state of charge, then those things will happen, and then you will have a fire. And also when you move the lithium ion to the anode, even for graphite, you can have a plating phenomenon happening there. If you have a lot of lithium ion going to anode at a low temperature, particularly, the dendrite can even grow with graphite. And once you have a dendrite, you are going to break, it pierces through the separator, reach cathode and short circuit. So a lot of processes happening, and therefore battery management system is very important to ensure that the batteries operate very properly. Sorry, what do you want to say?
Yeah. So how do different manufacturers manage this situation? So how to prevent? So we see the practice from the press. Different manufacturers battery have different performance. Performance are different. So why they are different? How they can prevent this happen?
My colleague at Imperial College maybe better answer this question, but I will try. I think the difference comes from, yeah, as I say, the battery management system. This is one issue. The first issue is when you manufacture batteries, although there's a same batch, there may be small variety within each cell. So this is the first issue. We bought, for example, some commercial batteries from commercial suppliers, and same labeling, same model, and when we test them at the same condition, they give slightly different storage capacity. So there are some small variation within that. And second, the battery management system rely on how well you can predict the performance of the battery along the cycle life. And maybe for some companies, maybe they have very good model to predict that battery performance, and so they can control the batteries more precisely and to prevent any unwanted phenomenon from happening. But other battery companies may not have that very accurate prediction of battery performance, and also that if we want to involve AI, a lot of data. Maybe some company use a lot of data to actually to get accurate battery performance prediction model, and some don't. Many issues.
Mike, there's one at the back.
Sorry, Mike. Long walk. Thank you very much for that explanation. Just a few weeks ago, I borrowed a book, it's issue 2 of this book, from Crawley Library. I was browsing the technology section, and it is, if you like, the notes, the study notes for technicians who are going to be looking after electric vehicles. And so it talks at length about the battery management systems, but more equally about the thermal management of the battery systems. So I think the questioners needs to have a look at that book because it's useful. It talks about the different batteries, about how they describe it, about the ways in which the batteries are configured for different vehicles. As I understand it, Tesla distribute the batteries all around the vehicle, and then have obviously a complicated battery management system, but maybe a limited thermal management system, whereas people like JLR and BMW package them in a crate, and then the crate is connected to a liquid cooling system, and that can often double as the heating system for the car as well. And so, it's quite involved. The technology's involved. Yeah, I mean, unfortunately, I can't remember the title. It's there in the library because I returned it a few weeks ago.
Yeah, well, thank you for that. That's a very good point. Yeah, indeed, thermal management system. There are several different thermal management systems. You can use air for cooling. You can use immersion cooling, so immerse your battery into liquid. And you can also have phase-changing materials for cooling. Different companies adopt different cooling strategy, and different cooling method has a different efficiency, and so on. That's also another reason. Yeah.
And maybe most importantly is the quality of manufacturing.
Yes, I would also.
That's a quality issue.
Thank you very much. Very interesting discussion. So back to your roots, chemistry. How do you determine a material that's suitable for battery use? Because you've listed off lithium, talked about sodium. What is it that makes the chemical attractive to battery? I mean, you've got power density. We had a talk during lockdown. Someone was talking about ammonia as a fuel for
Yeah.
planes. Is that a potential future battery material, for example? What would make ammonia not suitable?
Ammonia, well, we also do a little bit of work with ammonia, but ammonia work with fuel cells. Yeah, you can use ammonia to power certain type of fuel cells. To answer your question about what kind of material would be good, I think when Professor John Goodenough invented lithium cobalt oxide, he came from the solid state ionic background, physicist. And I think from his background, he knows that material has this kind of layered structure. The crystal structure is layer by layer, and therefore you are able to insert lithium ion into it. Similar for graphite. Graphite also has a layered structure, and that interlayer space is big enough to accommodate lithium ion. We actually, when we have synthesized a material, we probably don't have a very clear idea whether this is going to be a good material or not. But the first thing we would look at is their crystal structure first of all, or do they have a stable crystal structure? And then we will have to put them into half cell. So we make a bottom cell in like a bottom. They are very small in our glove box in our lab. We will then have to test them, actually cycle them and test them what kind of potential they have, and then how many cycles they can last. Yeah, we will have to do those kind of testing in order to know whether they are suitable or not. Yeah, but we can learn from the existing materials. The ones that are good, what kind of crystal structure they have, and if we could maybe make similar crystal structures, then probably those ones would be good. Yeah.
Okay, do we have a last question for this evening, perhaps? Because I think I'm sure you will, Mike. Does anybody else have a last question before we let Mike go? Okay, Mike, over to you.
Really, it's a comment. Well, first of all, thank you all so very much for a very interesting talk. And just
My pleasure.
to inform those of you who don't know, I gave a talk on home battery systems at the end of our last, before the summer. And I would just like to emphasize or add a little bit more to the question of battery management. It is absolutely crucial. The home battery system which I've got, which I described, is not a Tesla. And the battery management system is very different. It's a slightly different chemistry. It's a lithium battery, but it's a different chemistry. And the battery management system is significantly different from the Tesla. The software is quite complicated. For example, one very simple thing, when it was first installed, it was in a cupboard, and there was a shelf above it which actually had air holes, and on one occasion I had them blocked up, and the battery capacity suddenly decreased because the thermal management system couldn't get rid of the heat quickly enough at the crucial time. So that is the kind of thing that you have to take account of. And every battery system will have different software which is optimum for the battery. Anyway, thank you very much for
thank you for
the comment. Systems which will all require software and different management as a battery management system.
Yes, yes, indeed. Thank you.
And care not to block the holes in the shelf, Mike. Okay, well, John, thank you very much indeed. It was been a fascinating talk, and we'd like to give you this certificate in appreciation
thank you.
of your coming to the IET
Thank you so much.
and talking to us tonight. So thank you very much, everybody.